Hi, welcome to this short video that shows how to configure a dual loop system in TwinCAT with a Control Techniques drive. So the hardware that we've got is a laptop that's been loaded with TwinCAT XAE shell. It's also been loaded with Control Techniques Connect software. There's an Ethernet connection through to our Beckhoff hardware, which in this case is a Beckhoff IPC, but the steps would be the same whether it's an IPC, a PLC or a controller from Beckhoff. Now, one of the ports has been configured for EtherCAT connectivity, and that is connected through to an SI EtherCAT, which is then plugged into a Unidrive M700, making it an EtherCAT capable drive. But if you've got one of our dedicated servo products, such as Digitax HD M753, that drive has the EtherCAT interface built into it, so it's a EtherCAT capable drive off the bat. So for the dual loop side of this, rather than just a single motor on its own, in this setup, this is the rig that I tend to use for dual loop type setups. It's a Control Techniques dynamic servo motor where the feedback device is plugged into the P1 interface in the drive, and that encoder is used to control the speed loop. The P2 interface is connected to an encoder that's on the output shaft of this 5:1 gearbox. So there's 5 turns in from this motor to 1 turn out here at this position loop closing encoder. So just a quick overview of the loops. So we've got the current loop. Current loop takes a torque producing current reference which comes from the output of the speed loop. So any speed following error that we kind of develop during running, that appears as a torque reference which is then sent to the current controller to provide torque producing current to the motor. Then last in the line is the AMC position loop. So the AMC is the motion controller that's built into Digitax HD and into Unidrive M, and this essentially receives the reference from EtherCAT and then allows us to close the position loop on that reference. Okay, so in a normal system, so one that's not dual loop, you'll note that this feedback from the encoder on the back of the motor goes to close the speed loop and is also used to close the position loop. However, for the system that we're looking at, the speed feedback from the back of the motor is only used for the speed reference to work out what speed following error that we've got. This second encoder, the one that goes into the P2 interface, forms the position feedback. So we'll be looking for positional following error only based on this encoder, ignoring this one. Now, the upshot of this is that the speed reference that the position loop outputs needs to be scaled. This is simply because the speed that the motor this side needs to do compared with what this encoder will see the other side of the gearbox is the 5:1 ratio. So this motor needs to do 5 turns before you see 1 turn of movement at the output, and that needs to be compensated in the scaling. So that's what we're going to go set about doing in the demonstration. So there are 3 objects that you need to go and set up in your EtherCAT startup list. So the first of those is OX3000. Now what this object does is it says, where is the position loop feedback going to come from? Okay, so for what we're going to do, we're interested in using feedback that's plugged into the drive P2 interface. So we need to go and set this to a value of 2. So next, we need to set out the position loop output scaling numerator and denominator. Okay, so that's OX3004, subindex 1 is the numerator, subindex 2 is the denominator. And because our gearbox is 5:1, we need to increase the speed output from the position loop by a factor of 5, because our motor needs to turn 5 times as quick for one turn at the output of the position loop closing encoder. So you'll see that the value that we're going to set is 5 for the numerator to increase it by 5, divided by 1. Before we get too far into it, I just want to point out this document. So this is a kind of getting started guide that we put together to go along with this series of TwinCAT videos. And everything that you'll see in the video is covered by a section of this guide. So if you look, we've got how-to guides, how to set up a dual loop system. If I click that, this section of the manual follows along. So if you don't want to take notes whilst watching the video, or simply you just prefer learning from step-by-step guides in a book, we've got you covered. This book is linked in the description. So what I've done, I've already set up the drive, to work as a non-dual loop system, okay? And what we've got to do first is we'll add another encoder to our P2 interface, okay? So let's just open up menu 3, and I'm going to go to the second encoder parameters. So for the purposes of this experiment, I wasn't able to find a high resolution encoder, so I'm using a 1024 PPR incremental encoder, which is pretty low resolution, and you'll see that when we're looking at the following error, but I think it still demonstrates the point. So first thing, I need to go and set the number of pulses per rev correctly, which is 1024. I am then going to set, there we go, the type to AB, because it's just a simple AB quadrature encoder. And I think that's probably enough for now. So what we're going to do is we're going to come back to the performance tuning tool, and we're going to test to see whether this encoder is giving us a sensible output, and if it is it in the right direction? So let's check that out. So I'm going to take drive control, I'm going to enable it. I can hear that the motor is now enabled, and I'm going to add in an extra parameter. So I want the speed feedback from P2 so that we can take a look and compare. So what we'll be doing is comparing this feedback to this feedback, and what I'd expect is that the number that you get here will be 1/5 of the number that we'll see for our speed loop closing encoder. So let's take a look at that. So I'm just going to start the scope. There we go. So I'll just let that go for a sec and then stop the scope so that we can analyze. So what we can see is that the peak speed reached, using this green line here, for the speed loop closing encoder is 300 RPM. If I go back to the profile setting, you can see that when we were jogging, 300 RPM. So that's done its job. What we can see is that the P2 interface encoder, although it's 1/6, it's 1/6 and negative. And the simple reason for that is the mechanical installation of the encoder that I chose meant that I couldn't fit it in exactly the same orientation. And that's quite a common thing. You're limited to what mechanical fixings that you've got in your machine. So quite often you'll have to invert the encoder. So that's what we're going to do. So I'll go back to menu 3, and you will see if I go to this parameter here. Hold on. Just going to disable it and take off that control. I'm going to invert the feedback. So when you invert the feedback, you should do it with the drive disabled, because you don't want to cause a jump. So I've done that. I'll just save that. I'll come back and we'll test it again. So take control, enable the drive, start the scope, and run it again. Now what you can see, I let that button go and stop, the sign of the speed now matches. Okay, so we're getting 60 RPM for 300 RPM feedback. So both of them match, and they're both in the same direction. So now we can have a reasonable degree of certainty that when we close the loop, the position loop rather, with this P2 interface, that everything should work how it's supposed to. So I'm just going to disable the product. I'm going to release control. So releasing control will now enable us to take control once we've finished the configuration in the TwinCAT environment. So that's what we're going to do now. So the first thing that we are interested in doing is making our mappings in our startup list. So let's go to that. So what you want to do is click on the drive that you're going to change the scaling for so that you can do your dual loop. Select the startup tab. In fact, these are some old mappings. I'll go and get rid of those so that we can reapply them. There we go. And we go new. So if you remember, the first object that we're interested in is OX3000. So because all of the CT standard objects are actually listed in the ESI file that you would have loaded as one of the steps for setting up the axis, and this is all described in previous videos, you can just select it. And then what we're interested in doing is putting in a value of 2. So I'll click OK to that. So there we go. So what this has done is it said the position loop, instead of being closed by the speed feedback encoder, now we're telling it explicitly go and use the P2 interface for the drive encoder. Next thing that we're going to do is go set up the scaling numerator. So if I go in here, select scaling numerator. Now I need to set this to a value of 5, but one thing to point out is that whenever you're setting up anything to do with the startup list manually, it's a kind of quirk, if you like, of the EtherCAT spec and of this tool, that the way that you have to enter the information is in hex and in reverse endianism. So the difference is, if you've got conventional hex values, you would say that a value of 5 that's within a 32-bit value, the least significant byte would contain the value 5. So you'd express it something like this. It'd be 0, 0, 0, 0, 0, and then 0, 5. That would be the conventional way. But because this is reverse endianism, the byte order is reversed. So instead of the least significant byte being at the rightmost space, it's actually put in first, so it's at the leftmost space. So if I get rid of that, put it there. So it's something to be aware of whenever you're dealing with anything to do with the startup list. You've got to remember that the byte order is, you know, reverse endianism. And where that would probably come in is if you're doing some scaling and it's not just a simple 5-to-1 gearbox like I've got for my desk setup. It's something more complicated, like you are compensating for the scaling difference between a line encoder wheel and a pull roller, something like that. You might want to express those diameters in microns so you get the best possible ratio between the two. And when you do that, you'd probably have to convert those diameters in microns into a hex value and then rearrange the byte order so it becomes a reverse endianism value. There we go. So let's do the last one. So the last one is denominator, which in our case, sorry, that didn't go, be 0, 1. There we go. Okay, so we've got our position feedback selected as 2. We've got our scaling numerator to multiply the speed output by 5 over 1. There's our scaling. So next thing is we want to push that scaling in. So I'm going to activate the configuration. So push that over. Actually, there's one other thing that I need to do, so I'll have to do that in again once it's finished. The next thing that you need to do is compensate for the scaling that the gearbox gives you, and I'll show you what I mean. So here we've got the maximum reference velocity and maximum overall velocity, and this would be correct if we weren't doing a dual loop system with a 5-to-1 gearbox ratio in the way. So what we need to do is limit the speed that we request here to be the maximum for the motor, but also including the 5-to-1 gearbox ratio. So what we're saying is at the position loop encoder, we're only going to have 1/5 of the motor's maximum rating. So let's go through that process. So if I get my calculator, cancel all of that. So what we want to do, I'll just show you in here. If I go to references, we can see that our maximum reference clamp speed in RPM is 3000. Okay, so we need to convert from 3000 into units per second. So let's go back to our calculation. So if I look quickly at our encoder object, we can see that we've got 1000 units for 1 rev in this case at 19-bit resolution per rev. But the number we're really interested in is how many units we've got per revolution in order to do the calculation. So is this 1000 number that's actually of importance to us. So 3000 RPM, and then we need to go from revolutions per minute to revolutions per second, which is dividing by 60. And then we need to times by, because this is revolutions per second, we need to get to units per second. So we times by 1000. Okay, now that's okay if we were at 1-to-1 with our position loop closing encoder, but we're not. We are 5-to-1 ratio. So what we need to do is times 1 divide by 5. I'm only using the numerator and denominator here to show you what it would be like if you've got a more complex ratio. So 10,000. So that's what we need to go and set our maximum speed limit to. So okay, there we go. So I am just going to activate the configuration to push that setting in. So let the system sort itself out. Hopefully. There we go. Right, now you can see that after activating the configuration, that our revised limit that compensates for the gearbox is in there. So what we've got, I'm just going to push this program in. There we go. So I'm choosing to use from the CT&C axis library this function block, which is called MCCT position axis. So this is just saving me time from trying to couple a load of normal PLC open blocks from the NC axis library. So like MC power and MC jog, all I've got to do is plumb in the axis ref name and then enable the drive and get going. So that's what I'm using. There'll be other videos in the series that fully explain how to use this interface, but for now, essentially what this is doing is causing an MC move velocity to allow the axis to jog at 1 revolution per second, which is the same as 60 RPM. So let's do that. There we go. So I've just enabled the drive, I've given it drive on, and now I am gonna jog. So I can hear my motor working. Let's go and have a look to see what that looks like on our scope. So what we can see, in fact, because the maximum scaling looks a little bit strange, I'll just stop it. Just so it goes from 0 to our maximum. Otherwise you're not going to be able to see anything. There we go. There we go. So what we can see is that now we're actually controlling over EtherCAT. We've got the references that we expect. So it's 1 revolution per second or 60 RPM at our position loop closing encoder. Our speed reference to the product has been multiplied by 5, which is what we want, so that they match each other, and our speed feedback error is roughly 0. Now what I also need to do is include this, and what you can see is that there's no offset in the value of the error. If you've got your scaling wrong in some way, what you would find is that this overall value would be offset positive or offset negative. If you can see it, that it's roughly centered around 0, I wouldn't worry too much about 1 or 2 RPM because the position loop will soak that up. But if there's a reasonably significant error, then you probably want to have a look at your gearing ratio and make sure that you've actually got that correct. What you will notice here is that obviously the waveform is pretty rough because the position loop closing encoder that I had available that would fit my rig is only actually giving a true resolution of 4096 counts per rev. So, you know, normally it wouldn't be quite as rough as this, but it's just related to the particular hardware that I've used in this demo. So there we go. That's everything that you need to check for and how to set it up. Hope you found this useful. Thanks for watching.